separates the black hole from the outside world. The nature of black holes is studied thanks to Albert Einstein's general theory of relativity. The theory predicts that the mass of the black hole warps spacetime, forming a gravitational well. This deformation is so strong that it affects the trajectories of light and matter. For example, light passing near a black hole can be warped, forming an effect known as gravitational lensing. There are several types of black holes depending on their mass. Stellar black holes are formed by the collapse of massive stars and have a mass that is usually 3 to 10 times the mass of the Sun. Supermassive black holes are found at the centers of galaxies, including our own Milky Way. Their mass reaches millions or even billions of solar masses. Their origin remains a mystery, but they are thought to form due to the merger of smaller black holes and the absorption of matter over billions of years. Another category is intermediate black holes, which have masses ranging from a few hundred to several thousand solar masses. Their presence has only recently been confirmed thanks to modern observational methods, such as gravitational wave astronomy. The phenomenon of Hawking radiation adds another mystery to the nature of black holes. Stephen Hawking predicted that black holes are not completely black, they can lose mass and energy due to quantum effects, emitting weak thermal radiation. This phenomenon is explained by the interaction of particles and antiparticles at the event horizon. A single particle can fall into a black hole and the other escapes, causing the black hole to gradually evaporate. Space traps are also a place of extreme phenomena. If we imagine that an object falls into a black hole, it undergoes a phenomenon known as spaghettization. This is due to the difference in gravitational forces between the near and far sides of the object. Gravity is so strong that the object stretches into a long and thin thread. The study of black holes is carried out using various methods. For example, telescopes capture the X-ray radiation that is produced when gas and dust are heated to extreme temperatures before falling into a black hole. Gravitational waves are also used, fluctuations in spacetime caused by collisions of black holes. In 2015, for the first time, such waves were recorded, which was a revolutionary discovery in physics. These objects can interact with other objects in the universe. For example, they are able to absorb stars that pass too close, forming powerful accretion disks of matter orbiting the event horizon. In such cases, there is an emission of relativistic jets, jets that spread over thousands of light years. However, these cosmic craters are not only destructive. They may also play a key role in galaxy formation. Supermassive dark zones in the centers of galaxies regulate the processes of star formation, influencing the distribution and movement of matter. This relationship between black holes and galaxies is one of the most pressing topics in modern astrophysics. Gravitational collapse objects are also important for studying the fundamental laws of nature. They are laboratories for testing relativity, quantum mechanics, and their interactions. For example, the problem with the information paradox is that quantum mechanics requires the conservation of information, while general relativity assumes its annihilation in a singularity. This question remains unresolved and is one of the key mysteries of physics. The phenomena of space and time capture the imagination of not only scientists, but also a wide audience. They inspire science fiction, where they are often depicted as gateways to other dimensions or time machines. And although these concepts are hypothetical, they stimulate interest in the study of the universe. In 2019, the world saw for the first time a photograph of a black hole taken by the Event Horizon Telescope. This image was a confirmation of the theory of relativity and demonstrated the power of modern technology. Dark gravitational forces remain one of the most intriguing objects in space. Studying them opens up new horizons for science, helping us better understand the nature of the universe and our place in it. An incredible source of inspiration and research, so it is worth delving even further into aspects of their impact on space, physics, and our understanding of reality. One of the most interesting topics in the study of black holes is their effect on the surrounding matter and radiation. When material, such as gas, dust, or even a star, falls into the gravitational field of a black hole, it does not immediately disappear into the singularity. Instead, matter forms an accretion disk, a structure that consists of heated gas orbiting a black hole. Due to friction and gravitational forces, the gas in this disk heats up to millions of degrees, emitting energy in the X-ray spectrum. It is this radiation that makes black holes visible to astronomers, because they themselves do not emit light. Supermassive black holes, which are located at the centers of galaxies, are often accompanied by powerful jets of high-energy particles escaping from poles of the accretion disk. These jets can reach thousands of light-years and significantly affect the galaxy's environment. For example, they are able to expel gas from the galaxy, slowing down or even stopping the process of star formation. Such interactions are an example of how black holes can influence the evolution of galaxies and the formation of cosmic structures. In addition, they can merge with each other, forming even more massive objects. The merger of these astronomical objects is accompanied by the emission of gravitational waves, which were predicted by Einstein in his general theory of relativity. In 2015, it was possible to register these waves for the first time, and this discovery was revolutionary. It not only confirmed the theory, but also opened a new era in astronomy, the era of gravitational wave observation. Another intriguing topic related to these objects is their formation and growth. Although the process of stellar black hole formation is more or less clear, the origin of supermassive black holes remains a mystery. How did they reach such huge masses in a relatively short time after the Big Bang? There are several theories. One of them suggests that supermassive black holes form from seeds, primordial black holes that appeared in the early universe. Another hypothesis suggests that they grow by absorbing large volumes of matter or merging with other subjects of the astrophysical singularity. Even more exotic is the idea of primordial black holes, which could have arisen shortly after the Big Bang due to fluctuations in the density of matter. Such objects could have a variety of masses, including very small ones. If they exist, primordial black holes could explain some mysterious phenomena, such as the nature of dark matter, which makes up a large part of the mass of the universe but still remains elusive. The existence of these gravitational monsters poses numerous philosophical and theoretical questions to science. For example, is it possible to travel through a black hole? Theorists suggest that a black hole could be a portal to another universe, or even to another time. These ideas remain speculative, but they stimulate scientific research in the field of quantum gravity and the nature of spacetime. The paradox of information in black holes is another unsolved problem in physics. If an object falls into these space traps, all information about its properties seems to be lost when it reaches the singularity. However, quantum mechanics states that information cannot be destroyed. This contradiction has become one of the central questions in modern physics, and solving this puzzle could lead to a revolution in our understanding of quantum mechanics and gravity. Another mystery is the nature of the singularity, which is the central point of a black hole. In a singularity, the laws of physics that we know cease to apply. It is a place of infinite density and curvature of spacetime. Current theories such as quantum gravity and string theory try to explain exactly what happens in a singularity, but there is no definitive answer yet. These light absorbers also have a huge impact on popular culture. They are often depicted in movies, books, and video games as mysterious, dangerous objects, or as means of traveling through time and space. For example, in the movie Interstellar, the gargantua black hole became the centerpiece of the plot, and her image was created using real scientific models, making her one of the most accurate in cinema. In conclusion, black holes are not just mysterious objects that challenge our understanding of the universe. They are the gateway to new knowledge and understanding of how our space works. Studying them is not only a journey into the world of extreme phenomena, but also the key to unraveling the fundamental laws of nature that underlie everything that exists. Black holes remain the focus of attention of astrophysicists and theorists alike, because they open up limitless horizons for scientific research and reflection on the nature of reality. To further understand their essence, it is worth considering additional aspects, such as their connection to dark energy, quantum effects, as well as their role in the large-scale structure of the universe. One of the most exciting theories is the suggestion that black holes may be related to dark energy, a mysterious force that accelerates the expansion of the universe. Some current models put forward the idea that the vacuum energy that surrounds black holes could be a source of dark energy. If this is true, then these gravitational wells play a much larger role in cosmology than we can imagine. It also opens up opportunities for new approaches to solving one of the main mysteries of modern science: why is the universe expanding at an ever faster rate? The quantum aspects of black holes are one of the most active research topics. As mentioned, Stephen Hawking predicted that black holes emit energy through a process known as Hawking radiation. This process demonstrates the interaction of gravity with quantum fields and suggests that black holes can gradually lose mass and eventually evaporate. This phenomenon highlights the relationship between quantum mechanics and general relativity, but also reveals a deep contradiction between the two. These contradictions, known as the information paradox of black holes, stimulated the development of new theories, such as the holographic principle. This principle states that all the information that falls into a black hole is stored on its event horizon in the form of a quantum code. If true, then black holes could act as a kind of storage devices for information about the universe, which opens up exciting prospects for quantum physics. Objects with critical gravity not only destroy, but also create. They play an important role in the formation of galaxies and large-scale structures of the universe. For example, supermassive black holes can act as architects, forming galaxies through their gravitational interaction. Their ability to influence the movement of gas and dust around them creates conditions for star formation. In some cases, however, supermassive black holes can slow down this process if their jets cleanse the galaxy of the gas needed to give birth to stars. One of the most striking phenomena associated with black holes is relativistic jets, or jets. These jets are formed by extreme magnetic fields that are generated by accretion disks around rapidly rotating black holes. Jets contain charged particles that are ejected at speeds close to the speed of light. They are able to penetrate intergalactic space, affecting nearby galaxies and even creating shock waves in intergalactic gas. The study of jets helps scientists better understand not only the nature of black holes, but also the evolution of galaxies and quasars, extremely bright objects that gain energy from the accretion of matter onto supermassive black holes. And while black holes are often associated with destruction, they also open the door to ideas about traveling through space and time. In general relativity, the existence of so-called wormholes is allowed, hypothetical tunnels that can connect different points in spacetime. Although the existence of wormholes has not yet been confirmed, their study offers hope for the development of future interstellar technologies. Gravitational influence zones are ideal objects for testing new theories. They challenge our knowledge of high-energy physics, quantum fields, and gravity. Future research with advanced telescopes such as the Space Telescope James Webb, as well as new gravitational wave detectors, will allow you to penetrate even deeper into their nature. Black holes are not just dark spots on the map of the universe. They are the key to nature's deepest mysteries, from the beginning of time to the limits of space. Studying them not only expands our knowledge of the cosmos, but also raises fundamental questions about what it means to be part of this boundless and mysterious universe. One of the most interesting concepts is the idea that black holes can be energy sources capable of fueling the evolution of galaxies and even creating entire cosmic structures. The enormous amount of energy released during the accretion of matter exceeds the energy produced by stars, and this energy is capable of influencing the chemical composition and dynamics of gas in galaxies. This phenomenon, known as active galactic nucleus feedback, can stop star formation or change the ways in which new galaxies form. Quasars, one of the brightest objects in the universe, are an example of such processes. They are powered by the energy released during the accretion of matter onto supermassive black holes, and their brightness can surpass the glow of all the stars in the galaxy combined. Observations of quasars allow scientists to study the conditions that prevailed in the universe in the early stages of its evolution. Dark matter is another mysterious substance that makes up about 27% of the mass energy of the universe, but does not emit light, so it cannot be observed directly. Black holes are often seen as candidates for the role of reservoirs for dark matter. Although research has not yet provided definitive answers, there are theories that black holes can interact with dark matter particles, creating unique gravitational signatures. For example, if primordial black holes formed in large numbers in the early universe, they could be major components of dark matter. However, this idea remains speculative, since no clear evidence of the existence of such objects has yet been found. Observations of black holes that existed several 100 million years after the Big Bang raise questions about their origins. How were they able to reach such masses in such a short time? One possible answer is the direct collapse hypothesis. In this scenario, large clouds of gas could collapse directly into the black hole, avoiding the star formation stage. Another option is accelerated growth due to the efficient absorption of matter. The study of early black holes allows scientists to better understand the conditions that prevailed in the young universe, including the formation of the first galaxies and stars. Imagine two black holes orbiting each other, gradually getting closer. This process is accompanied by powerful gravitational waves, fluctuations in spacetime that propagate at the speed of light. When two black holes merge, they emit huge amounts of energy in the form of gravitational waves. The first such waves were recorded in 2015 by the LIGO Observatory, which was a revolution in physics. These events not only confirmed the existence of black holes and mergers between them, but also opened up a new way of studying the cosmos. Gravitational waves allow us to hear the universe, allowing us to study objects and phenomena that are inaccessible to conventional telescopes. One of the biggest challenges of modern physics is the unification of two fundamental theories, quantum mechanics and general relativity. Black holes are at the junction of these two sciences, which makes them ideal laboratories for developing new theories such as quantum gravity. For example, the question of whether information that falls into a black hole is stored remains a central problem in physics. If this problem is solved, we can get the key to a theory of everything that will unite all the fundamental interactions of nature. Even though black holes are associated with the end, they can also be the key to the future. There are ideas that the use of energy released during the accretion of matter can provide humanity with an almost infinite source of energy. Such ideas remain fantastic, but they highlight the importance of black